This video will cover Chapter 7 out of the Gabrosek Stephenson textbook. Chapter 7 is about matched pairs data, where we have some sort of pairing with the data that we collect, and our data has been observed in natural pairs. So the term pair data means the data has been observed in natural pairs. Some examples of this. Each observational unit is measured at two different points in time. The example that I like to use here, especially if we're in class, is the freshman 15. And then I would ask someone, hey, what is the freshman 15? And, well, it means that freshmen typically gain 15 pounds their first year at college. And I'm really interested in whether or not the freshman 15 exists. So what I'm going to do is I'm going to get one of those Biggest Loser scales. Freshman orientation, we're going to march up all the freshmen, and it'll go beep, 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 and then it'll like cut to commercial as someone's like gasping and stuff like that, because that's how it always happens. But anyway, we will measure all of the weights of the freshmen at the beginning of the year. At the end of the year, we will march them all back up. They'll be much more tired, and it'll go beep, 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 beep again, and we'll record their ending weight. I do not care what their beginning weight was. I do not care what their ending weight was. I care if there's a difference between those two, and if the difference is 15, well, then you're helping to perpetuate this freshman 15. I don't want to call it a myth, but stereotype, the freshman 15 stereotype. So the key thing here is we have two different measurements taken, and something happens between those two. And here, freshman year happens between those two. And I should note that I'm not actually applying for a grant for one of these Biggest Loser scales, but this is a great example of paired data. Another example of this type would be we could measure everybody's 100-yard dash time in whatever shoes you're currently wearing. I could give you all the latest and greatest Nike Air Shock Maxes or whatever is out right now. Measure your 100-yard dash time again. I don't care what your first measurement is. I don't care what your second measurement is. I care if there's a difference between those two. The second type of paired data, each observational unit has two different measurements taken simultaneously, and I do say simultaneously like that because it doesn't have to happen at the exact same time, but nothing has to happen between the two measurements. We could measure hand spans and figure out what your right hand span is, what your left hand span is. I don't care what those are. I care if there's a difference between those two. We could talk about the human body being square or squarish in terms of measurements, where we measure your height and we measure your wingspan. I don't care what your height is. I don't care what your wingspan is. I just care if there's a difference between those two. So again, we have two measurements. We don't care what the actual measurements are. We care if there's a difference between those two. The last type of paired data that we'll talk about here in class, observational units are placed into logical pairs and differences are recorded within pairs. I used to work at Pfizer in the animal health division, and one of the drugs that I was responsible for running numbers on dealt with pigs. And one of the things we were concerned with was that pigs continued to gain weight, so that pig farmers could sell them for more money. Something else that's true about pigs, though, smaller piglets grow up to be bigger pigs. And we wanted to make sure that our pigs were continuing to gain weight on our drug. So what we would do is when the little piglets came in, we would take the largest two piglets. We would randomize one of them would get the drug and the other one would get a surgical procedure. We would take the third and fourth largest piglet. We would randomly assign one the drug and do a surgical procedure to the other one, all on down the line. Now, we didn't care how much weight pig 1 gained or pig 2 gained. We didn't care how much weight pig 3 gained or pig 4 gained. We cared, well, what's the difference between those two? And we wanted to make sure that the pigs that received our drug grew just as well as the pigs that had the surgical procedure. So again, in this case, we don't care what one measurement is, we don't care what the other measurement is, we care if there's a difference between those. So whether each observational unit is measured at two different points in time, each observational unit has two different measurements taken simultaneously, or if observational units are placed into logical pairs and differences are recorded within pairs. In all three of these examples, we have two measurements, and we're talking about the difference between the two measurements. And so those paired differences, and this is the worst definition that I will give you all semester long, but paired differences are the differences recorded within pairs. So it is these differences. We have our two measurements. What is the difference between those? Section 7.4, confidence intervals for the population mean paired difference. As with any confidence interval, any statistical inference, there are required conditions. We do need a random sample, or at least a sample that avoids bias. And because we're dealing with means, if the data is normal, any sample size will suffice. Otherwise, we need at least 30. And now you might think, well, don't we need 30 from both populations then? And I will tell you, no. We only have one population of interest. We have two measurements, but they're both taken on the same population. So for our freshman 15 example, in order to be part of this data set, I need a beginning weight and I need an ending weight. For the height versus wingspan, I need your height and I need your wingspan. For our piglet example, I need pairs of data. In all these cases, we have two measurements, but the important part is not the measurements themselves, but rather the differences recorded within the pairs. So there is only one group, there's only one sample size to consider, and if the data is normal, doesn't matter what the sample size is. If the data is not normal, or if you don't know if it's normal, you need to make sure that you have at least 30. We do need a quantitative variable, again, because we're talking about means. We have to have a quantitative variable if we're going to take an average. And the last thing, which is kind of trivial, if you're doing stuff on paired data, that means you have paired data, but we do need paired data. Our sample estimate here is going to be d bar. This is the sample mean of paired differences. So you have your beginning weights, your ending weights, your height, your wingspan, the first piglet, the second piglet. You find the differences between all of those data points, and d bar is the average of those differences. It's the sample mean of all of our paired differences. Our multiplier that we use here, because we're dealing with means, is a t-star multiplier, and the standard error is s sub d over the square root of n, where s sub d is the sample standard deviation of the paired differences. So our basic formula for a confidence interval for the population mean paired difference, we have d bar plus or minus our t-star multiplier times s sub d over the square root of n. Now this is very, very, very close to something that we've dealt with in the past. I'm going to take you back to chapter 3 for a moment, where we did a confidence interval on one population mean was x bar plus or minus our t-star multiplier times s over the square root of n. What we're doing here in chapter 7, this is essentially the exact same as what we did back in chapter 3. The only change from what we did back in chapter 3 is the type of data that we're dealing with here. Here, the data that we have is the differences between two data points. Once we have all these differences, we can find the sample mean of all those differences, we can find the sample standard deviation of all those differences, and this just turns into a one population mean problem. Once you have your paired differences, that's just the data that we're using, and this essentially becomes chapter 3 material. So again, the only change, instead of just dealing with quantitative data, we're dealing with the difference between two quantitative data sets, and once we have that, it turns into something that we already did. So once we get to this point in this chapter, the rest of this is technically a review, because it's stuff that we've done back in chapter 3. So the example we'll use here, the 35 students in a liberal arts course in statistical literacy. Man, that sounds like a fantastic class. They were given a survey that included questions on how many hours per week they watched television and how many hours a week they used a computer. If you're watching Netflix on a computer, I don't know how you're supposed to answer that question, but this was probably done before Netflix. The sample mean difference, computer use minus TV use, was 3.36 hours. The standard deviation of the differences was 15.24 hours. Calculate a 90% confidence interval for the average difference in hours spent using computer versus watching television for the entire population of students represented by the sample. And then answer the question, is there a statistical difference between computer and TV use? So D bar is 3.36. That's the sample mean of the differences. S sub D is 15.24, the sample standard deviation of the differences. Our standard error, we take 15.24 divided by the square root of 35, and we get 2.576. Our T-star multiplier, we go to our T-star multiplier table, we use 34 degrees of freedom, looking for a 90% confidence interval, and our T-star multiplier is 1.691. We plug all three of these things into our overall basic formula for a confidence interval, which I don't give you again, but it's always the same. Sample estimate plus or minus a multiplier times our standard error. Had to check if I did give it to you. So yeah, 3.36 plus or minus 1.691 times 2.576. The low end of our confidence interval is negative 1.00. The upper end of our confidence interval is 7.72. Now something that I don't ask you here, but something I could ask you, is for you to interpret this confidence interval. I'm blank confident that blank is between blank and blank. So I'm 90% confident that the difference between computer use and TV use among all college students is between negative 1 and positive 7.72, or I'm 90% confident that mu sub D is between negative 1 and 7.72. I don't think I've defined mu sub D. Another piece of notation, what we're trying to even do a confidence interval on for the population mean of paired difference. So we've got mu represents our population mean, and then sub D means differences. So we're finding a confidence interval on mu sub D. So we are pretty sure, we're 90% sure that mu sub D is between these two values. Is there a statistical difference between computer use and TV use among all college students? Well, no. This is an example where 0 is in our confidence interval, which means mu sub D could equal 0. It's plausible that mu sub D equals 0, and there is no difference between computer use and TV use. Hypothesis test for the difference, or the population mean of paired differences. Same 5 steps: assumption conditions, formulate your hypotheses, calculate your test statistic, find your p-value, and report your conclusion. The assumptions and conditions, not surprisingly, are the exact same as what we needed for a confidence interval. We need a random sample. If data is not normal, we need a sample size of at least 30. We do need a quantitative variable, and we need paired data. Our hypotheses. Our null hypothesis is just mu sub D equals 0. So not only is this a special case of a one population mean problem, it's actually easier, because we can always just write it just like this: mu sub D equals 0. For this class anyway. Now, if you're out to disprove the freshman 15, you would probably put 15 in here, but you don't need to worry about that for my class. We'll just say mu sub D equals 0. Our alternative hypothesis will be one of these three, depending on what we're trying to prove. Mu sub D is not equal to 0, or mu sub D is less than 0, or mu sub D is greater than 0. The usual caveat that we always talk about: if this is your alternative hypothesis, you may use mu as greater than or equal to 0. Mu sub D is greater than or equal to 0 as your null. If this is your alternative, you may use mu sub D is less than or equal to 0 as your null. Step 3, calculate your test statistic. Again, we're calculating a t-statistic because this is a hypothesis test on means. Sample estimate minus the null value divided by the null standard error. So our sample estimate is d bar, the sample mean of paired differences, minus our null value of 0. And this is why not only is it a special case, it's actually easier because our numerator is just d bar. And then our null standard error is s sub d over the square root of n. It's the same as what we used back in our confidence interval. P-value. Use our table. Use our chart. Remember, this is essentially a one population mean problem. You have your test statistic. You have your degrees of freedom. Find where those meet, and the table gives us our two-tailed p-value. If you only want one tail, you divide by 2. And then step 5, report your conclusion. If the p-value is less than 0.05, we reject the null and accept the alternative. If the p-value is greater than or equal to 0.05, we fail to reject the null and fail to accept the alternative. So let's perform a hypothesis test to determine if the amount of computer use is different than the amount of television use for all students. Spoiler alert, we should not find significance here because in our confidence interval we said that they were not significantly different, so we shouldn't find significance here either. Are the conditions met? Yes, they are. It doesn't matter if our data is normal because we have a sample size of at least 30 and it's random enough. There's no inherent bias for students taking a statistical literacy course in liberal arts or something like that, whatever the class was. So we'll say yes, the conditions are met. Our null hypothesis mu sub d equals 0. There is no difference between computer use and TV use among all college students. Our alternative hypothesis is mu sub d is not equal to 0. There is a difference between computer use and TV use among all college students. Our test statistic, we have d bar, which is 3.36. We have s sub d over the square root of n, which we've already calculated. We don't need to recalculate it because it's the same as the standard error we used in our confidence interval. So 3.36 divided by 2.576 gives us a test statistic of 1.304. We go to our table. We use 34 degrees of freedom, round down to 1.30, and our p-value is 0.202, which is greater than 0.05, which means it's not significant. Like I said, it shouldn't have been significant. And we fail to reject the null. We fail to accept the alternative. There is not enough evidence to prove that mu sub d is different than 0. There's not enough evidence to prove that computer use is different than TV use among all college students. And that's Chapter 7.